Welcome to this video, which is going to examine a new unit of measurement for angles called Radian Measure, and we will look at the connection between angles measured in radians versus angles measured in degrees, and we will draw a conversion factor between the two so that we'll be able to convert angles in radians to angles in degrees. As you move up through your pre-calculus courses, the more advanced you get into pre-calcs and moving towards calculus, the unit of measurement, the preferred unit of measurement, becomes radian measure for angles. So it's going to be really important that we are able to become competent working with this measurement. I find students a little bit reluctant in the beginning. They still want to work everything in degrees just because of the comfort level. So you have to kind of push yourself outside that comfort zone and try and make yourself more comfortable and confident with radian measure. Okay, so here we go. Radian measure is defined as one radian is defined as the angle subtended by, that means opened up to, so this angle here is equal to 1 radian if the radius of the revolution is equivalent to the arc length. So if this was like a piece of string and I snipped it off here and I laid it out flat, it would be identical in length to this. That's referred to as 1 radian. Well, 2 radians would mean this. This angle in here would be measured as 2 radians. And 2 radians would mean that the arc on the outside is equal to 2 times the measurement of your radius. So for example, if I had a circle like this that had, let's say the radius was 3, let's say that was a 3, and I drew this out here, and I told you that this arc on the outside was 15, and I said, what angle's that? Well, if we look here, if the arc was double the radius, the angle was 2 radians. If you look at the connection here, this is 5 times whatever the radius is. So the arc is 5 times the radius. So back here, when this was twice the radius, we said this was 2 radians. So that tells me that this angle would have to be 5 radians. You can abbreviate these in radians to RAD, or as we get going with this, you can actually leave that out altogether. And if you're talking about an angle, if there's no little degree symbol here like you've seen in the past, it will be understood you are implying that it's in radian measure. So it becomes important that you somehow indicate whether you're talking about radians or degrees. Well, we're going to take that little kind of discussion we just had and turn it into a formula. If I said to you, is there any way to calculate theta if you know the arc and the radius? All right, so I just did one where, well, we'll scroll up here. So I knew this, and I knew this, and I calculated my angle. So the angle of rotation in radians, now this only holds true in radians. It's a dangerous formula to show students because then they say, oh, that's a neat formula, and they use it all the time, and then they end up using it in situations where it actually isn't true. It's only true in radians only. If you take your arc length and you divide by your radius, arc length divided by your radius, you generate your angle in radians. So the nice thing about this is that it allows us to quite easily calculate an angle measured in radians. Now, if I just rearrange that formula, let's suppose I was trying to calculate the arc. Well, just like any formula, you can rearrange this. So the arc would be the angle in radians multiplied by the radius, which is what this little box has here. I always like to get students to remember the formula, though, at this level right here. Start from this. Your angle in radians is always equal to your arc length divided by your radius. One thing to watch for is to make sure these are always measured in the same unit. So if this had been in, let's say, centimeters, and this was in meters, you'd have to do a conversion to get those in the same units. Before, let's just do a couple of quick circles here and let's do some calculations. So let's suppose that I had, that's not what I wanted. That's a polygon. All right, I just got a couple diagrams set up for us here just to show you how that formula works. So remember, an angle in radians is always equal to the arc length that is subtended by that angle. Subtended to means opened up by. So this angle opens up to that arc. So there's your arc. If I wanted to calculate, in this case, theta, it would simply be the arc length, 18, divided by the radius, which is 7. They're both in centimeters. So my angle would be 18 over 7 radians. That would be it. Now in this one, I know the angle in radians, and I know the arc. I'm trying to figure out the radius. So theta equals A over R. I'm just going to substitute now and then rearrange after. So theta is 1.8 radians. Can't stress enough that this has to be an angle in radians to use this formula. The arc is 12 centimeters, and radius is our unknown. So if I multiply both sides by r, I'm going to have 1.8 r equals 12 centimeters, which tells me that my radius will be 12 centimeters divided by 1.8, and that will give me my angle in, my radius in centimeters. I'm just going to grab my calculator. I just grabbed my calculator. So this one, if we do the actual calculation on it, didn't say anything about rounding, so we'll use our standard 3 decimal places that we generally use. So this one would be 2.571. I don't have to write radians if I don't want to, because I haven't used a degree symbol. It indicates I'm talking about an angle in radians. Now this r is the radius, so I'm going to need 12 divided by 1.8, which will give me 12. Divide that by 1.8, and I will get 6.6 repeating, so 6.667 centimeters. That would have to be the radius of that circle if that angle is going to measure 1.8 radians. All right, so that just kind of shows you how you can calculate and use this important formula when you're talking about a rotation. Now, this is all going to come back to play, and we're going to talk about angles, and they're going to be angles that are rotated on a Cartesian plane, but we're just kind of building up toward that, but that's where this is all going. It's on things that we're going to rotate around a Cartesian plane or a graph. Okay, so let's see if we can establish a connection between degrees and radians. Well, if I look at that, let's take some things we should know about a circle. Let's suppose I had a line that cut through the center of a circle. We should know this angle in degrees. This angle in degrees should be 180 degrees, because we know that if we go in a full circle, there are 360 degrees. Well, if I go to let's go back to this formula, theta equals A over R. This works in radians. Well, if I do a calculation of this angle right here, which I know is 180 degrees, but I'm going to calculate it using this formula, the formula would be the arc. This is your arc on the outside here. Actually, I'll use my highlighter maybe. So this is my arc on the outside. Now my radius is just this value here, so my radius. So I'm just going to do this algebraically, meaning this distance here, if you recognize it, is 1/2 of the circumference. Well, let's just write out circumference first. So the circumference of any circle is 2 pi multiplied by the radius. Well, the yellow part I've highlighted is half the circumference. So half the circumference would just be 2 pi r divided by 2, which is just pi r. So I know then this arc that I've highlighted in yellow, that arc would have to be pi r, half the circumference of a circle. given that its radius is r. So I'm going to do a calculation using this formula, filling in my arc, which is pi times r, divided by my radius, which is the letter r, and I want you to notice what happens. These two cancel out, and I have just calculated my angle to be pi radians. However, I knew before I started that that angle in degrees was 180 degrees. So we have now just established a very important connection in radian measure. Pi radians is equivalent to 180 degrees. So that is a conversion factor. Just like you knowing that there's 100 centimeters in a meter, you now need to know that pi radians is equivalent to 180 degrees. And again, can't stress enough. So at this point, I've already identified two things students have to know. You have to know that theta equals a over r is a way to calculate an angle in radians, and I now have to also know that pi radians is equivalent to 180 degrees, which I have here. This would just be if you took your conversion factor and just got it down to what they call unitary version. The unitary version is simply taking, let's say I wanted to get 1 radian. Well, to get 1 radian, I would divide here by pi, and whatever you do to one side, you have to do the same thing to the other side, which would now say that 1 radian is equal to 180 over pi degrees, which is what I have there. And if I wanted to do the other way, so I would take my same relationship, pi radians, and I know that it's 180 degrees, but I want to know what 1 degree is equal to. Well, I divide this by 180, divide this by 180. So now I know that pi over 180 radians would be equal to 1 degree. So that's where these came from. It's just reducing this connection down to its unitary values. Personally, I think if you just know this, you will function just fine in converting angles between the two different units of measurement. You may recall at some point that your calculator gets switched into a mode called radians. So there is a mode, which really doesn't come into play until we get into trigonometry. But if at some point you remember your teacher saying, oh, make sure your calculator's in degrees and not radians, well, you're getting to the point now where you're going to finally see what was this whole radians bit they were talking about. So that's kind of the journey that we're on right now, is we're getting ourselves familiar with this whole concept of radian measure. Okay, so let's take 60 degrees, and I was trying to figure out what 60 degrees is in radians. Well, I'm going to take 60 degrees, and I'm just going to use my conversion factor. My conversion factor says that there's 180 degrees in pi radians. So my degrees are gone, and I'm now left with just 60 pi over 180. Now this is where it's really nice to have that fraction button on your calculator, because we're going to get a lot of fractions doing this way, and we're going to, for the most part, leave them in fraction form. So we're just going to reduce 60 over 180 and say that that is pi over 3 radians. Now if you think about this, pi radians is equivalent to 180 degrees. So if this is 180 degrees, and I divide it by 3, 60 degrees. Well, that would make sense. So to convert degrees to radians, it's always very simple. You just multiply by pi over 180. So if I said, oh, I've got a 10-degree angle. Well, 10 degrees, you multiply it by pi over 180, and you will end up in radians, get rid of your degrees. So that would now be 10 pi over 180, reduce 10 over 180 to pi over 18. And that would be in radians. I'll eventually stop writing this out. I just want you to realize that we're doing a conversion from degrees to radians. So this would kind of fall in line with what you did in GMF 10, where you convert it units. I could have things like 300 degrees. 300 degrees would be 300 degrees. Multiply that by pi radians over 180 degrees. And now I've got 300 pi over 180. And ideally, if I have a fraction button on my calculator, I can just type in 300 over 180, hit the equal sign, and it will reduce that fraction for you. Or you're going to have to kind of work your way through it and say, well, I could divide this one by 60 to get 5 pi, this one by 60 to get 3. So there's 5 pi over 3 is also 300 degrees. If you wanted the decimal version of this, you would actually have to use your calculator and go 5 times 3.14, you know all the deal, it goes with that, divide it by 3, and you could get the decimal equivalent of this. Now, we stay in this format more often than not, just because this is exact, versus once you get to here, you're going to be having to round off your answer, just because pi is irrational. But in this case, you'd actually use the value of pi. Now, I find sometimes students in the beginning of this will say, well, now you're really throwing me off. You used to tell me that pi was equal to this. Now all of a sudden you're telling me that pi is equal to 180 degrees. No, what I'm telling you is pi radians converts to 180 degrees. But pi is always 3.14128. All right, so I don't want you to think that I'm doing anything different with that. Oops, sorry. All right, so that would be degrees to radians. So of course we want to be able to go the other way. So if I had, well, I'll start with the easy ones. If I had 3 pi over 2, and I wanted, that's in radians, and I wanted that to be in degrees. Well, if they give you the angle in terms of pi, it doesn't get any easier than this, because I know that pi radians can be just swapped out for 180 degrees. And now I just go 180 divided by 2 is 90 times 3. This angle was 270 degrees. Pi over 6. I know that pi is 180 degrees. Divide that by 6. This must be talking about a 30-degree angle. Well, it doesn't matter. Let's say I had... We will also get into negative angles. I could have a negative 7 pi over 4. Well, this is going to be negative 7. Replace pi with 180 degrees. Divide that by 4. That's 45. So that's going to be... I'll grab my calculator here for a sec. 180 divided by 4 is 45. Multiply that by 7. So it's going to be negative 315 degrees. Now, it's not always given in terms of pi. So you might be given something like this. So let's suppose they give you, I don't know, 7.46 radians. And you're wondering what that is in degrees. Well, you should always kind of have some kind of a reference as to what kind of an answer you should be expecting. I want you to realize that pi, which we know is 3.14 radians, is equal to 180 degrees. 2 pi, now when you think about that, 2 pi, so double that, is 6.28 roughly radians, and that is a full circle, right? Because pi was only 180 degrees, which is half. 2 pi, double that, is 360. So if I'm looking at this, 7.46, I should be getting a number that's more than 360. So hopefully that's what will happen. And now, like you would have done in NERF 10, I would set up a conversion factor. I'd say I want to get out of radians, and I want to end up in degrees. And say, okay, what's the connection between them? There's pi radians in 180 degrees. So I'm going to go 7.46, multiply it by 180. I'm going to divide that answer by pi, and we should now then be in degrees. So let's see what I get here. 7.46, multiply that by 180, I get 1342.8, and then I need to divide that by pi. 427.42, let's just round this. So let's go 427.4 That would be the degree version of it, which at least that is reasonable, because I know that 6.28 radians is 360 degrees. That's more than 6.28, so my answer should have been more than 360, which it is. So there's how you convert an angle that doesn't have, it's in radians, but it doesn't have it in terms of pi. It just has it as a decimal value. That's the method I would use to convert that. So if you wanted to look at, let's say, another version of that. Oh, I think I've got a few examples here. Let's just jump ahead. Oops. Okay, so let's look at a few of these. Let's take 90 degrees. 90 degrees would be 90 degrees times, so the conversion factor, I want to get out of degrees and into radians. So there's pi, I'm going to leave it blank, that means it's in radians, which would give me 90 pi over 180. 90 over 180 reduces to pi over 2. And if we think about this, in degrees, pi radians is 180 divided by 2. There's your 90. Some of these angles we're going to use a lot. They're called special angles, so you'll get used to them. That was A. Let's pick D. So D is 45 degrees. And you can kind of start speeding this up a little bit once you kind of get the hang of this. Say, well, all I got to do is multiply by pi over 180 every time to go from degrees, and I'll be in radians. 45 over 180 reduces to 1/4. This would be the angle pi over 4. If I had 120 degrees, 120 degrees would be 120. Multiply that by pi over 180. So I've got 120. Sometimes you'll see it written this way too. I'll just show you, and then they'll kind of stick the pi out beside it. That's the same thing. That's fine. You reduce 128 over 180, which reduces to, divide them both by 60, so 2/3 with the pi written there, or this would be the same thing, 2 pi over 3, like so. All right, so that's a couple more degrees to radians. Let's look at a couple of these ones now that are radians back to degrees. Now these are the easy ones because they have pi in them. I don't know, let's pick ones we haven't done already yet. Let's try 4 pi over 5. So that's F. So 4 pi over 5 means 4. Convert pi radians to its degree equivalency, which is 180, over 5. So now I got to go 4 times 180 and divide by 5. Let's see what I get. 4 times 180, divide that by 5. I get 144 degrees. Oops. That is 144 degrees. Pi over 10, so h pi over 10. Convert pi to its degree equivalency, which is 180 degrees, divide by 10. So we are talking about an 18-degree angle. As I said, those ones are easy. This one wants us to go from degrees to radians, but it wants our answers to 2 decimal places. So let's take 49 degrees. Nothing changes. Same method. 49 degrees would be 49 multiplied by pi over 180. The only difference is we're actually going to put this in our calculator now. 49 times 3.14, blah, 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 over 180, and we're going to carry our answer to 2 decimal places. So if I just put that in my calculator here, it is 49 times pi, and then divide that by 180. And that would be 0.85, 2 decimals, 0.86, and I would now be in radians. Which, again, it's reasonable, thinking that 3.14 radians, or pi, is 180 degrees. So I'm talking about 49 degrees, which is significantly smaller than 180, so I should be getting something smaller than 3.14, which I did. If you wanted to try 200 degrees, and you wanted the decimal equivalent of it, it would be 200 multiplied by pi over 180. Throw that into your calculator, and that would be 200 multiplied by pi, and then divide that by 180, 3.49. Oops. And that would be in radians. I've rounded it off, so I put a dot over my equal sign. 3.14 is 180 degrees, so this is slightly higher than that, 200 degrees. It all makes sense. So there, I only did a couple of examples. I did B and D. Next examples are when you're in radians without the pi. So let's pick B. So if I had 2.1 radians, and I wanted to convert that to degrees, so again, use your conversion factor. I'm in radians, I want to get out of radians and end up in degrees. Well, I know there's 180 degrees in pi radians. So now I simply multiply, and it wants one decimal place. So 2.1, multiply by 180, and then divide by pi. So 2.1, multiply that by 180, and then divide that by pi. 120.3 degrees. I'm going to try D, which is 1 radian. So 1 radian times 180 degrees for every pi radians. So this is going to be 180 divided by pi. So 180 divided by pi. Your answer will be in degrees. So if I go to my 180, divide that by pi, 57.3 degrees. Make sure with degrees you put your little degree symbol up there, because if there's no symbol on an angle measurement, it is understood or assumed you're talking about an angle in radians when there's nothing there. All right, so that's how you work between the two units. You now see what the connection is and how to switch between the two. So now we'll kind of begin our journey actually using this stuff to do some things. This is all going to eventually lead us into some trigonometry, but before we get to that, we still got a few other things we want to look at. So that's where we're going to go next. So I'm just going to look at two examples here of how you could use radian measure and angles, looking at rotations and that kind of thing. First thing I'm going to look at is a pulley system. So this pulley system has two pulleys, a bigger one and a smaller one. And it just asks us a series of questions here where we're going to, for the most part, rely upon this formula. Theta equals A over R. And use that to answer a few questions about this. So it says if the large wheel rotates through 2 pi over 3 radians, so that means this is the large wheel. The angle here it's going to rotate through is 2 pi over 3 radians. So the question then is, well, what angle is this wheel going to, not angle, sorry. Yes, it is. How many radians will the smaller wheel rotate through? There's a couple ways to do this. I'll show you both. The first way is, let's figure out what the arc would have to be to rotate through 2 pi over 3 radians, because I know that theta equals arc over radius. We know the radius and we know the angle that the big wheel is going to turn, so we should be able to figure out the arc it spun on the outside, or how far the belt traveled. Theta is 2 pi over 3 radians. The arc, I am not sure, but I do know the radius is 10 centimeters. So in order to solve here for the arc, I'm going to multiply both sides by 10. 20 pi over 3, I'm going to be in centimeters, is going to be my arc, or distance traveled on the outside. So I'm going to just do that as a calculation. So 20. Multiply that by pi, and then divide that by 3. I will get 20.944 centimeters as the arc. That's telling me, that in order for me to rotate at the center an angle of 2 pi over 3 radians, I had to travel a distance on the outside of that many centimeters. So I just calculated the arc. So once you know the arc, we'll think this is a continuous belt running around this system. I now know then that if this belt traveled that many centimeters here, it traveled the same number of centimeters on the outside of this wheel. So what I now know is I know the arc of this wheel is the same as the arc of the other wheel, which would be 20.944 centimeters. So if I wanted to calculate the angle, theta, that it spun through in order to travel that distance, I would go to my formula, theta equals arc, 20.944 centimeters, divided by the radius, which was 4 centimeters, and that will give me my angle in radians. So I'm at 20.944, divide that by 4, 5.236 radians. Well, any of you that are mechanically inclined may have heard tell of gear ratios or pulley ratios. That's another way to do a question like this, where you just simply look at the pulleys. Now, if you had, think about this system. As the belt rolled around here, and this angle, or this wheel turned, this smaller wheel is going to have to turn faster to keep up with the bigger wheel as the belt spins around it. Well, if you do it as a ratio, the ratio is that this wheel, if you take 10, you just divide the two radius, and the ratio here is 5 over 2, or 2.5. What that means is the small wheel has to turn 2.5 times as fast as this one does to keep up with it. So another way to do that same question would have been, say, okay, the first one, I knew it turned 2 pi over 3, so the big wheel, rotate it 2 pi over 3. Well, the small wheel has to rotate 2.5 multiplied by that. And if we multiply that out, we should get the same. It'll give us the angle, which I was looking for. So 2 multiplied by pi, and then divide that by 3, and then multiply that by 2.5, and we get 5.236. Look at that, same answer. So that's using what they call a ratio system. As I said, some of the mechanically inclined people will understand how that works with pulleys and gears and that type of thing. And if you kind of get the gist of that, you could do it that way. Now, if you're going the other way, you'd have to divide by 2.5, right? Because this one's going to go slower than this one, versus this one, the angle should be bigger. So if you just always keep that in mind, the smaller one has to rotate more to keep up with the bigger one, if you're going to do it with that system. So the second question says, the large wheel completes 3 revolutions. How much does the small wheel rotate in radians? So the large wheel went 3 revolutions. So part B. 3 revolutions. Now the first thing you should do is change that to an angle. 1 full revolution. Think about something going in a full circle. Well, that angle in degrees is 360 degrees. But in radians, that would be 2 pi radians. Well, if it makes, so now I'm going to do my angle then, because every 1 revolution is 2 pi radians. So I know that the large wheel is going to rotate 6 pi radians. So you got 2 options. You could go through the same calculation you did here, knowing theta, knowing the radius, calculate the arc, take that arc over to this formula, fill it in for your arc, divide by your radius, you will get your angle in radians. Or let's do this one with the ratio system. If the large wheel rotated through that many radians, the small wheel would have to rotate 6 pi times 2.5, because of the ratio of the 2 wheels is 2.5. And now I would get, that's my value here, 6 times pi and then multiply that by 2.5, I get 47.124 radians. So that would be the angle. I think that's what they asked. Let's double check on that. Yes, so how many radians did the small wheel rotate through? I just did it using my ratio system. It would have to be 47.124 radians. The small wheel rotates a negative 15.4 or 15 pi over 4 radians. How many radians does the larger, spelled wrong, wheel rotate? Let's ignore the negative because I haven't got to discuss that with you guys yet. Let's suppose that that's a positive, because there actually is a difference between positive and negative angles, which we'll discuss later on. So the small wheel is 15.4. All right, so this time, small wheel, theta is 15 pi over 4 radians. Well, to go from the small wheel to the big wheel, you would have to take the angle that this one rotated through and divide by 2.5. Or, conversely, you could, because you know the radius of this wheel, let's do it, I'll show you the other way. So the other way is take your formula, theta equals A over R, fill in your theta, 15 pi over 4 equals the arc over the radius. The radius of the small wheel is 4 centimeters. Solve for arc. So the arc here is going to be, multiply both sides by 4. That'll get rid of that. Multiply this side by 4. That gets rid of that. So it's 15 pi centimeters. Let's leave it like that, actually. That's exact. So that's the arc, which means distance traveled on the outside. This is arc. So the arc traveled here will be the same as the arc traveled on the big wheel. So now I'm going to go to the larger wheel, and I'm going to calculate the radius. Sorry, not the radius. Calculate the theta, knowing the arc. So now on the big wheel over here, theta is arc over radius. This is the arc, 15 pi centimeters. The radius on that one is 10, and that will give me, that's in centimeters. So when I divide these, I should divide these both by 5, 3 pi over 2 radians. That would be the angle of rotation of the larger wheel, which is smaller than 15 pi. All right, so that's understanding that connection between the arc, the angle of rotation, and the radius. Now, one thing we have to kind of make ourselves aware of is that, I know on a circle, let's say, we think of the arc perhaps as a piece of the circle. Let's say that's called an arc. But in theory, when we're doing these questions, an arc could be like 6 trips around the outside of your circle. That could be the arc. And then you could get an angle, but all it would mean is that your angle is more than 360. So if your angle is like 1200 degrees or 27 pi radians, you would just use that to figure out how many times or what distance you spun around the outside, what arc was traveled on the outside. So I don't want you to think of it necessarily as a little piece of the circle. It could in fact be multiple trips around and then some of the outside of a circle that we would refer to as the arc. Okay, last connection I want you to make is how to come up with the area of a sector. All right, so looking here, we're trying to get the area of this little shaded piece out here, which is kind of an irregular shape, not something we have a formula for, so we're going to have to come up with a plan for this. In this, we're going to have to use a couple of formulas. So one thing we're going to have to know is how to get the area of a circle. Well, hopefully you know that the area of a circle, these are formulas that you would not be given, is pi r squared. Well, this thing here, if you have like a wedge of pi, that's called a sector. So the area of a sector would be that angle. You basically want to figure out what fraction of a full circle is this. Well, in a full circle, I know there's 360 degrees if I'm in degrees. So if I'm in degrees, it would be theta out of 360, and then you'd multiply it by the area of your circle. If I was in radians, so this is degrees, in radians, it would be still the same thing, theta over, instead of 360 though, you'd have 2 pi here for your radians, multiplied by pi r squared, which actually very nicely gets rid of that, don't forget your squared. So in radians, your formula is just theta r squared. This is the area of a sector. And you say, what the heck is he talking about, a sector? This is a sector. Right, that out to there and out around the outside. So that's how you get the area of a sector. It's a fraction. So what fraction of a full circle? Theta to 360. So that out of a full circle gives you what fraction of a circle it is, knowing that a full circle has an area of pi r squared. So in radians, I just did the conversion. Instead of 360, I put 2 pi here, which nicely crossed those out. And oh, I should have over 2 there. Sure, some of you were yelling at the screen as I was screwing that up. It should be theta over 2, because the 2 is still left here, times the radius squared. And that will give you the area of that sector. Well, if I want to get the area of the shaded part here, I'm going to have to get the area of the sector, but then I'm going to have to subtract the area of this triangle. Now, often students say, oh, I know how to get the area of a triangle. It's 1/2 the base times the height, which is fine if you know the base and the height. But there's another formula for the area of a triangle students should know, which you may or may not already, but if you don't, here it is, and make sure you learn this formula. So area of a triangle, and this is used if you know 2 sides and what they refer to as the contained angle, which is exactly what this diagram has. 2 sides and the contained angle, the angle that those 2 known sides make up. Well, to get the area of that triangle, it is 1/2 AB sine of the angle between the 2 sides. So we're going to use this formula and one of these two, depending on what we've got. Right, this is the degree version of it. And this would be the radians version of it. And our plan will be to find the area of the sector, which is the pie-shaped piece, find the area of the triangle, and then if I subtract the 2, I should be left with what they call the area of the segment. That's what they call a segment. A segment is made up of a piece of an arc and what they refer to as a chord. Okay, so here I go, and see if I can put all this to play. So let's start with the sector first. So I'm going to go sector area. And my area is, well, before I can get to any of that, I need to know that angle. I don't know the angle. So students say, well, how am I going to do that? Well, nice thing is we have a formula, theta equals A over R, that will let us calculate this angle in radians. So the arc is 15 divided by the radius, which is 10, which is 1.5 radians. Now I know the angle. It's in radians, so I'm just going to leave it in radians, and I'm going to do my sector area using this formula. Theta over 2 times your radius squared. Well, theta is 1.5 radians over 2, and the radius, I believe, is 10. Now, they don't put any units on it, so we won't put any units on anything here. And the area will be 10 squared is 100, divided by 2 is 50, so 50 times 1.5 should be 75. Now, I'm just going to say units squared, because I don't know what they are. They didn't tell me centimeters, meters, or whatever. Now, that's the area of the sector, the piece that looks like that. Now I'm going to go and do the area of the triangle. And the area of the triangle, which obviously we know what a triangle looks like, it would be this triangle inside here that I'm going to get the area of. So the area of that triangle is 1/2 AB sine of theta, where A and B are the 2 contained, the 2 sides, and theta is the angle between those 2 sides. So I'm going to go 1/2 A, which is 10. Your other side is 10 sine of my angle, which is 1.5. All right, so now here is a key issue here with a calculator. So the calculator issue we're going to run into is this angle is in radians. So do you remember in grade 10, grade 11, your teacher telling you make sure your calculator is not in radians? We're going to now tell you the opposite. Make sure your calculator is in radians if you're putting a radian angle in here. Now if you put a degree angle in here, you'd want your calculator in degrees, but I have entered a radian measure angle. Now how do I do that? Well, unfortunately from here on a video it's hard for me to do that, but there's usually a variety of ways. If you have a mode button, sometimes you repeatedly hit that mode button and it'll come up and you'll see a screen that'll say something like degrees, and it might put a 1 beside it, and then it may say radians 2, and then there's even another one called gradians that'll have a 3, so that's telling you hit the number 2, you'll switch to radians. Some calculators have a button like this. They'll have capital D, capital R, capital G. There'll be a little triangle beside it, and you just repeatedly hit that and look up on your screen, and you'll see on the screen it'll be switching. There'll be a D highlighted, then there'll be an R highlighted, then there'll be a G highlighted. Keep hitting it over and over till you're in the right one. Hopefully you'll be able to figure out your calculator and how to get it switched from degrees to radians and back and forth, because we are going to work back and forth between the two. As a last-ditch effort, you could always Google the model number of your calculator, how to switch it, and you could, I'm sure you could easily find it on there. But you do have to figure out how to switch your calculator back and forth now between radians and degrees. So in Radian Measure, if I do this calculation out, area would equal so it's going to be, trying to do this on my phone, which isn't a great calculator, so bear with me here for a sec. All right, so I just want to double check something here for a second. Yeah, we're good. I did the sign of 1.5 first, just to make sure. So just to double check on your calculator, I got 0.9979 was the value for that. And now I'm just going to multiply that by 100, 10 times 10, and then I'm going to divide that by 2. 49.875. That would also be square units, whatever the unit of measurement would be. So that's the so I found the sector. I just found the triangle. I'm going to get the difference between these two to get the area of my segment. So here goes our segment. And the segment, in case you're wondering, so I don't know what the heck he means by the segment is this piece up here. So to get the area of your segment, you're going to take the sector, and you're going to subtract the triangle, and you will come up with the area of 25.125 square units. All right, so that is taking some formulas that may be new to you. Certainly take note of these formulas. Make sure you have them written down somewhere. Formulas that you need to know. These are formulas that students need to know as they work their way through the pre-calculus stream of things. So they're not formulas that we give to you. Okay, here's one. I'm going to try and find this red area up here. So again, you may want to pause and just watch. Watch the video. And now, one thing I noticed this time is this angle is given in degrees. So the fact that that's given in degrees, I think we're probably better off using the degree versions of our formula. There's no sense switching that to radians. Let's go and get our plan underway. So let's start with the sector. So the area of the sector would be theta out of 360 multiplied by pi r squared if I'm in degrees. So 74 out of 360 multiplied by pi multiplied by the radius squared. Now this time they did give us a unit of measurement. It's in meters. So I'm going to go 64, so 8 squared, times that by pi, times that by 74, and then divide that by 360. These calculators on the phone are terrible, but that's all I got right here where I am. So 41.329, that would be in square meters. All right, so I've just found the area of this shape with a 74-degree angle here and 8 meters out here. Let's go to the triangle. So the triangle I want is this one, 8 by 8 with that in the middle. So the area of a triangle is 1/2 AB sine of theta. So let's fill in our measurements. Oops. So the area of this triangle would be 1/2. A and B are both 8. And the sine of the angle between them is 74 degrees. So this is good practice now to switch your calculator from radians, get it back in degrees, because you're dealing with an angle in degrees. That's the only time whether you're in radians or degrees matters, is when you hit trig functions. So sometimes students say, oh, maybe I got the wrong answer because I was in radians. Well, unless you hit a trigonometric function, sine, cosine, or tangent, it makes no difference whether you're in radians or degrees. But this one, it would, because I'm doing a trig ratio. So I'm going to go get my calculator on my phone, I guess. Get back to degrees now. 74, and the sine of 74 is 0.9613. I'm going to multiply that by 64. I get 30.760. That would be in square meters. So what we're looking for is the segment. The segment is the difference between those two. So it will be 41.329 square meters minus 30.760 square meters, giving me an area for that segment of so minus 10.569. Square meters. Okay, so we're going to end that video. So two things: how to make the connection between, now that we know what radian measure is, how to switch between radians and degrees, and then how to use your formula theta equals A over R, and combine that with maybe some area formulas that I've talked about in the last couple of slides to kind of intertwine this whole radians and degrees and some measurements in something that's rotating in a circle, and finishing off with these area calculations that we just did. So have a look at your practice questions. Reach out if you run into any problems, and there will be a formative to go with this particular section. Thank you for watching.